Why do I need to know this is one of the most used questions in education. We learn for the test. But tests don't help with everyday life, we learn by practice. There are lots of videos on YouTube about learning related topics, but I find them either incorrect or incomplete. So in this video, I'm going to dive deeper and explain it from a different perspective. Here are the scenarios. In a cognitive scenario, I'm learning how to add. In a movement scenario, I'm learning how to throw a dart. A traditional approach for teaching addition would be to show a worked example, and then do lots of practice tests. But we can go deeper into the science. Before we can add numbers together, we need to be able to read the numbers, understand the relation between those numbers, like their sequence, and the skill of writing, speaking, or showing our answers in some way. In cognitive psychology, there are scientific theories that look to explain this learning process. Cognitive psychologists look at the mental processes that go on using findings from neuropsychology, which studies brain-damaged patients. Findings from computational cognitive science, which look to create algorithms for the steps our brain takes, and findings from neuroscience, looking at behavioral studies and neuroimaging. The main idea is that our brain, like a computer, processes information. Serial processing, often referred to as bottom-up processing, goes through stimulus, attention, perception, thinking, decision, and then response. The processing is directly influenced by the environment, the stimulus, and you need to get through the process before the next can be started, like waiting in the line, waiting for your turn, and some processes take longer than others. So we see the equation, pay attention to the equation, we perceive what the equation is asking us, we think, problem solve, find an answer, and share the answer. But that is oversimplified. When reading the words in this triangle, you likely read Paris in the spring, not Paris in the spring. The second "the" was not expected, meaning you used expectations and prior knowledge to skip the second "the." Like seeing a person that has ordered the same thing before, you guess what they will say. So instead of starting at the stimulus, the bottom, we could start with expectations, the top, which is top-down processing, which can be done at the same time, leading to parallel processing instead of serial processing. More than one process going on at once. These processes aren't always in sync, which is cascade processing, loads of orders being thrown into the kitchen at different times. This information processing approach is what memory models are created from. When looking at the multi-store memory model, can you see a potential issue? From sensory store with attention to a short-term store and rehearsal to long-term store. We use the long-term store in top-down parallel processing, so it should be a non-linear process. Long-term memory isn't at the end, it's also at the start and the middle. The unitary store model suggests short-term memory temporarily activates long-term memory, but we know it also stores information, so short-term and long-term memory need to interact. Working memory, some of you will be saying. The phonological loop is your internal voice for storing and mentally rehearsing information, writing down the order or saying it over in your head. The visuospatial sketchpad is your visual cache for visual form, like size and dimensions and color. The episodic buffer stores the information being used from long-term memory, using your training to prepare the food. They all interact with the central executive, which is an attention system that doesn't store anything, it just points your attention at something. A key assumption in this model is that if tasks use the same component, they can't be performed together successfully. A chess study illustrates this very well. The control group had players recall a chess position. Then the three test groups were given tasks to do during the retrieval. One group had to say "the" in time with a metronome, one group had to push a pattern of key presses on a calculator, and another group had to generate a random string of letters of the alphabet and say it out loud. As the chess recall requires attention and memory, we need the central executive, for attention, and the visual store for memory. So the tasks that used those components got lower results. You can't take more orders if everyone is already taking one, but other types of information are not considered in this model, like smell, touch, and taste. Spatial working memory could be eye, hand, or foot centered, which could lead to unpleasant amounts of components to consider. In addition, the visuospatial sketchpad has been shown to work with other components, like the central executive, suggesting a coupling or merge of components. Then the idea of a central executive just doesn't quite work, because we need to identify the different processes and functions that happen in attention. What do we do? Looking at executive functions, they have an inhibition function to prevent distractions, a shifting function to switch between tasks or mental sets, and an updating function to add or take away things in working memory. We add things to working memory as we perceive information, but research suggests we have a capacity limit, so we need to remove things. The limit is debated despite the 7 items being commonly promoted. The 7 items or 2 to 4 chunks of information don't help that much, as a different chess study illustrated well. A master group, expert group, and control group were asked to recall a chess game position and a random piece position. The masters had larger chunks helping them in the game position, but didn't have larger chunks for the random position. So 1 chunk from the expert memory doesn't equal 1 chunk from the control group memory. So 1 doesn't equal 1. In addition to that, priority can be put on the chunks, which can be altered by the environmental cues. Forgetting that thing you were thinking of because someone said something and you needed to pay attention to what they were saying. So memories could be displaced by new ones, decay over time, or interfered with by other memories. Retrospective or prospective interference. The working memory capacity limit research is more likely to reflect fluid intelligence, which is someone's ability to rapidly understand novel relationships rather than a numbered limit. We still group information together, but that group is different for everyone because we all have different prior knowledge. Putting this all into our adding scenario, we perceive the environment, pay attention to it, and then process that information. Once the processing in working memory is done, we act by sharing the answer. But where does an issue potentially lie in this modern representation of learning? We have stimulus in the environment, attention, processing, whatever that means, and the action, the perception of information in the environment, top-down parallel processing, uses long-term memory. We need another arrow. Putting this into our dart scenario, if we have thrown a dart before, we are using our experience, long-term memory, to perceive our environment. If I haven't thrown a dart before, we could use read-around knowledge, stuff that is similar, like throwing literally anything, or watching others do it, to help us perceive the environment. The grouped information, chunks or schema in long-term memory, are impacting our perception of the environment. Seeing it a second time is different. This brings us to the Bayesian brain hypothesis, where essentially we use prior beliefs, or experiences, to update the probability of something happening. The idea is that we use predictive processing after perception to update the likelihood of an action. A decision model using information processing could look something like this, which has the situation, a choice of processing which uses the Bayes rule of prior beliefs, expectancies, and other related information that leads to a decision of action. So it is still a linear model, stimulus, process, action, but Bayes' rule brings in some cycles introducing elements of non-linearity. Going back to the original question, why do I need to know this? The reason is that the perspective I lean towards doesn't follow the information processing approach, which is what I just went through. In other words, the things that I do to remember what I learn are implemented differently, but for reasons that wouldn't make sense unless you understood information processing. So the information processing approach, or IP approach, is one way of thinking from cognitive psychology, and the ecological dynamics approach, or ED approach, is a different way of thinking from ecological psychology. I don't see this perspective or science shared on YouTube as much, but in academia and coaching, some argue it is not a true dichotomy, which I want to discuss. Here is an overview. The term ecological dynamics is an approach using concepts of dynamical systems to understand things at an ecological scale. Systems are groups of parts separated from the environment, like a country with all the people, political, educational systems inside the international environment. The political system inside the country is a different system in the environment of the country, so it is a system in a system. These can be open or isolated, but most are open, meaning things flow in from the environment, adding parts to the system. Like putting coal into a steam engine system with an output of moving. But if the input isn't helpful, so instead of putting coal, put sand in the steam engine, it produces entropy or waste instead of a useful output. An unordered system is just a set of elements, but if they are ordered through relations, then we get an emergence of an organized system. Car parts on the ground are an unorganized system, but when put in relation to other parts in a specific way, it creates a car, just like organs of a human. Now let's add complexity by adding organization without centralized control, so no instructions for the organization of parts. Now we get self-organized systems with a new emergence or structure, which interact with other systems, with self-organization and emerge and so on and so on. A business is local, which contributes to national and then the global economy, each system being interconnected and interdependent of each other. Putting parts of a system together doesn't add the attributes to make a sum. The result can be very different. There is non-linearity in the emergence of the structure. Take the production line that Ford introduced to manufacturing. He was producing more with the same amount of workers as others because of the relations between the people and their work. The parts in the system were used together with a different outcome. The feedback loops in these systems can create significant change later on, known as the butterfly effect from chaos theory. You can see examples all over the internet where one situation or event completely changes someone's life later down the line. A system's connections form a network-like shape which represents a complex system. But in complex systems, there is no top-down control of parts of a system. They have autonomy for self-organization, creating the emergence of patterns from the bottom up, i.e. elements, through the systems. And as each element has autonomy, there is a wide range of possibilities that can emerge, with ecosystems and multicultural societies being good examples. The elements are subject to evolution and are selected if they suit the macro environment. If not, they fade away, move, go, etc. Products selected and bought are produced more. Politicians are subject to selection by voters, and animals subject to natural selection. In essence, the system is self-organized by the demands of the macro system rather than centralized coordination. These dynamical system concepts applied to a relationship between an individual and their environment is part of the ecological approach. The other part is the idea of direct perception. With the information processing approach, the assumption is that there is not enough information in the environment, so we need to process things. We sense or pick up cues from our environment, then perceive them, interpreting the information for Bayesian-like processing. Direct perception, on the other hand, from Gibson, suggests the information from the environment is enough to act. We don't need to interpret or process anything. Sensation and perception being the same thing. The reason this distinction is important is because indirect perception says we need to make a prediction, make a guess about what will happen in the future, predictive processing. Direct perception suggests we don't need to predict the future, but focus our attention on the information available at the time. This is an example clip from a program about Ronaldo scoring from a football cross in the dark.
It's almost as if they're doing maths in their head, even though they wouldn't be able to describe it to you.
They are talking about indirect perception and Ronaldo doing lots of predictive processing in his head while he can't see, whereas direct perception suggests he stopped gaining information when it went black, and because of online prospective control, he could still score. The online information, so information during the event of the cross being kicked, was enough for Ronaldo to score in the dark. Prospective control suggests he didn't use a memory store of past experiences to predict where the ball was going to go. He knew because of the way the person kicked the ball. You could argue the novice couldn't find success because of reduced experiences, so their predictions were off. Or you could argue that Ronaldo has a better calibrated or attuned sense of the information that he received before the lights went out. Ronaldo paying attention to the player kicking a ball rather than just paying attention to the ball, like the novice did. Both ideas, indirect and direct perception, explain the events, but fundamentally are different. Prospective or predictive control. When we take these perspectives, ecological with direct perception and prospective control versus information processing with indirect perception and predictive control, different ideas appear inside of learning. In the IP approach, people tend to talk about linear learning, like the classic Fitz and Posner model where you say lots of attention, refine movement, then it becomes automatic. So your skill model is getting more and more efficient. Better chunking, faster retrieval, better encoding, things like that. And the action is the thing at the end after all the processing. In the ED approach, it is non-linear because people are exploring and adapting to the environment, because we are self-organized complex systems in dynamic environments. We can take big jumps in learning and even go backwards. Perception and action are coupled. Acting isn't an end. We perceive to act and act to perceive, and decisions emerge from the ongoing control of action. The direct perception of online information gives us affordances, so we perceive opportunities for actions we can do, not just abstract things that are available to us. The IP approach generally has educators push a correct technique. Not exactly the same, but consistent fundamentals and structure. In our adding scenario, the educator gives an instruction. This is how you do it. The learner repeats the method, gets corrected to the solution the educator gave, and there is little room for individuality. Our dart throwing scenario, you get given instructions, body motions of how to do it. Then you repeat the method, get told you're wrong according to the educator's method, and again with little room for individuality. How do you do it if you have a long arm, a short arm, you're tall, you're short, etc. The ED approach doesn't think there is one correct technique. We need to create a set of solutions that suits our own individual constraints through self-organization as a system. Just like natural selection and voting for system selection, we select the skill by the environment we create through constraints of a task. We are attracted towards a solution because it suits us in the environment we are in. If the environment changes, the solution may change. So we learn to adapt to our environment with our various solutions rather than adjusting the best technique to a new environment every time. The IP approach traditionally repeats the same thing in practice. Then you learn to adjust to the environment you move to. So variability in practice comes later, once you have learned the fundamentals. So you only learn what is in the competition practice environment or what is on the test. The ED approach looks for adaptability instead, so you learn to act, bringing in variability as early as possible to encourage exploration and limit the development of inefficient attractors or solutions later on. This could include conditions that are not necessarily competition or test focused, but help with self-organizing solutions and developing problem-solving skills. Expertise from an IP perspective is traditionally knowledge about the skill. The better you understand the skill in your head, the better you will be able to perform it. This also suggests modularity in the skill, so you can break things down into small parts and put them back together once you understand them individually. To me, just because you understand the theory doesn't mean you can apply it in practice. And from my research and understanding, breaking a skill down, like throwing a dart into parts like working on the elbow action or the wrist action and putting them back together, won't necessarily lead to a good dart throw either. From an ED perspective, expertise is knowledge of the skill. The skill is not in your head, but your relationship with the environment. The more calibrated or attuned you are to the information in the environment, the more intelligent the learner-environment interaction is. So you can be good at something, but not know how to explain it because it is a different environment of expression. Instead of the skill, you are talking. And as you are doing the skill, you don't need to put things back together, you are learning what you are going to be doing. So both approaches from cognitive psychology and ecological psychology use similar educational tools, but apply them in different ways because of the views they have about cognition, specifically perception. Moving away from the science and scenarios into my personal application of remembering what I learn, this is my perspective and how I think about it right now. Active recall is a pointless term because you can't passively remember something, so you are just recalling something, which is retrieval, i.e. remembering. Spaced repetition is just one element of practice. But I don't do retrieval practice because to me, I am attuning my skill, knowledge, through practice. I don't test myself for memory retrieval, I create environments where ideas, concepts, and actions emerge from my self-organization using online information during the ongoing control of action. My practice is not about getting the best or right answer, it is about finding a variety of solutions in the environment I am in at that time. You can see this in the evolution of my notes, where each concept is evolving from the different environments I create with each project I do. This is attuning my skill and knowledge around that concept each time the information goes online during an event of me working in the note. My attention to the information on the page is different with each look. Now, I didn't cover everything in this video because of the complexity, time, and my own meta-ignorance, but hopefully I have exposed you to a different perspective of learning. If you're interested in my research workflow, there is a link to my Obsidian Focus course in the description. There is also a link to my notes for you to browse through, and I want to say a big thank you to all of my Patreons for the support and feedback during my research journey.